Yeah, thanks everybody for being here. So yes, like my title's a little pedestrian. Yep, we had 5 labs, we had 5 vendors. But really, the title of my talk might as well be, what's the point of measuring cannabinoids? And are we doing it right? I've tried to leave a little bit of time at the end for some questions and answers so that we can discuss. But first, I have to start with thanks, and the thanks start with CannMed. So Chris and I were just talking about how this is a great conference with a whole lot of really awesome people, and it seems like every single talk and every panel is a big hit. So yeah, thanks a lot for the opportunity to talk here. And then, specific to this project, there are a few people who I have to acknowledge, especially at the beginning. The first one is Josh Sweeter, because this project actually started because of him. He initiated this, and really throughout all the work, he was like the motor that was driving it forward. And then the next person I have to acknowledge is Joe Konchnik. Joe has now retired from ResTech, but he in many ways, was like the calm and steady voice that led each meeting that we had as we were working through this study. And so I feel like he was the steady hand at the tiller while Josh was the motor. And then I want to acknowledge Ginny Glaros, because she was really patient with me and helped a lot as I was trying to solve some very pernicious problems in data alignment. And make sure that our graphs were actually the right graphs. So I couldn't have done it without her. And then I have to also acknowledge Ava Hamilton, who did a bunch of the initial data cleaning and got the code set up so that then I could do all the processing, basically. Yeah, with that, I will tell you that this is a really big collaborative project, and we couldn't have done it without all of the people and all of the organizations that you see here, and it's a lot, all right? There are a lot of testing labs, a bunch of providers of CRMs, really a lot of people, a really big project. And the thing that I want us to be thinking about as we go through this is really the whole process of testing cannabis products in general. And is it fit to purpose? And if so, what purpose and who are we doing these measurements for? And what do we want out of these numbers? All right. And so we'll maybe, if you start thinking now about different kinds of product categories and what you expect from each one, that could be kind of helpful. So to start with, I'll talk about cannabis flower, because I think it's still kind of the prototypical cannabis product for many of us. And I think that we're all aware in this room that there is some variance between the buds of cannabis, and because those buds are they're an agricultural product, right? They're produce. Each one actually has its own level of total THC that I would measure if I measured it each individually. And I'll show you how I measured these, because that process is actually also very prototypical wherever you do it. So I actually measured those numbers in my living room, but you can... it's really, the process is shockingly similar and hinges on the same basic things, no matter how you do it and where. So first, you got to break up the cannabis somehow, right? And you got to have a good, accurate mass of it. And the precision of that mass is going to directly correlate with the precision of the final result. Then you're going to, you got to get the cannabinoids away from all that leafy stuff, right? So you always add some kind of solvent, some liquid that the cannabinoids will dissolve into, and then you shake it up a bunch to make sure that it gets done. And then you're going to inject that liquid into some instrument, and that instrument is going to do some kind of process, and it's going to produce some sort of a trace with some little bumps on it. And the area underneath those bumps is going to be proportional to the level of a given compound, and the position of each bump is going to tell you which compound it was in some kind of a trace. And then you're going to have this kind of hokey step where you have to figure out how to correlate that area with a particular number that's a concentration. And it's the way that we do that is with reference materials. Those are dilute solutions of organic compounds sealed up in little glass vials and shipped all over the world. And depending on the nature of that molecule that's in there, this could be like a better or a worse way to do things. So the challenge is that dilute solution is an unusually vulnerable situation for an organic molecule. So as I've drawn you here to kind of dramatize it, and probably not to scale, by the way. I think that at these concentrations, the molecules are even further apart. But this kind of gives you the sense that there's really isolated THC molecules, and they're totally surrounded by a sea of solvent that could, and even the tiniest parts per million of any contaminant could be enough to change things. So it's a pretty vulnerable situation, and it turns out that many of the cannabinoids of interest are also relatively vulnerable molecules, as we kind of consider, So that's a really important step. And so we did this study to try to evaluate, all right, well, how well is that working? And so in order to do that, we set up a collaboration with 5 manufacturers who contributed a total of 32 products. So those products included 18 singles and 14 mixes, and some of the mixes contain 5 or up to maybe about 10 compounds. So in total, and also a few of these, for a few of these products, we actually had, they include 2 different lots of the same product. So we had a number of different ways to analyze across parameters. And overall, we measured the concentrations of 127 compounds. And we did that in 5 labs. And then, actually, the labs didn't just measure this once. They measured each one a lot of times. So first, they set up their calibration, and all 5 labs synchronized to calibrate to the exact same lot of the exact same product. So that was the baseline to try to have everyone starting from a similar point as possible. And it's very important to appreciate the way the error is convoluting as we add on all these things, because we're sort of in this situation where we never have a ground truth, right? Like, we don't have one CRM that we know is made the best. So we have to choose arbitrarily to correlate, and then we have to hope that everything pans out well enough after the fact that we can actually pull apart the error. And it turns out that we're pretty much able to, partly because we measured a lot of points. So our procedure then for testing each sample reference material was that we would crack open each sample, we would do a dilution to get it to a concentration that was amenable to analysis. A few of these sample reference materials were actually formulated at such a concentration that no dilution was necessary. All right, and that was interesting and useful, it turned out. So, and then those dilutions were each performed 3 times, and each of those solutions was injected 3 times. So each lab provides 9 measurements of 127 compounds. All right, and then we take that times 5. So that's how many data points we have. And then we've got to sort it all out. and figure out if the results mean anything. So to start with, right, we can look at the results this way, where I plot on the x-axis like every single compound that we measured, and I use colored dots to represent the result from each lab. And then there are these little diamonds that show you the certified value. So what we did basically is for each sample, we back calculated the concentration that we determined that it actually was in the ampule, and we compared it to the certificate that came with it. So that's the data that we're showing here. So according to a calibration that we have all synchronized, we've measured each of these, and then we see each lab turns in their result, and we see how close they came. And it turns out that they come pretty close to each other, all right? I've normalized all these results, so the certificate value, that open diamond then, is right at 1, and all 5 of the lab results are those colored dots, and what you can see is those colored dots are often coming in, right? There's a reasonable spread between them. They're often coming in spread out by about 5% of the value to 10% of the value, more or less, right? It depends a little bit on the sample, but that's pretty much what we see, all right? So we can kind of hold that in our minds as like as a first kind of hand-waving measure of what sort of variance we see from lab to lab, all right? And we'll come back to that later. So one of the first things that's interesting to think about is, if you're trying to narrow down different sources of variance between different certified reference materials, how were our results as we aggregated them? How did our results come out for measuring products from the same company that supplied our agreed upon calibration standard? All right, and so what I've done is I plotted that here, and I plotted it in terms of I've actually aggregated just the variance and just the results from averaging all 5 labs results, and then counting up how many results came in within different bins of about 2% width. So what you're seeing here is that nearly all the results came in within 2%. So when we were back calculating concentrations, they came in within 2% of the certified value. All right, so and the average deviation, which tells you about, like, say, systematic error, it's the simplest measure, was only about 0.2% or minus 0.2%. So which is, I guess, what you would expect, right? I guess you would expect that the company that makes all of these would formulate them all pretty consistently with each other, right? All right, so that's pretty good. And then we have like a modest root mean square deviation or standard deviation. That's telling you that standard deviation is telling you something about the random error that comes from the dilution of all these products and then measuring again, mostly. So if we look at all of the results binned out in the same way, so again, on the x-axis, I've got sort of the number of compound results. This is a really quick and dirty way of summarizing a lot of data. Then I see that there are, all right, again, 127 compounds, right? The average deviation is still pretty small. So that's telling us that the agreement of formulation overall between companies or between vendors that we tested wasn't super large. But the root mean square deviation is like quite a lot more. What that is telling you is some of these were really badly formulated. And we can really tell the difference, right? Because the results from all 5 labs are really tightly clustered compared to these errors. So we know that these errors are associated with the CRM sample in question and not with the labs. So here's what these results mean, all right? So I've binned them out in terms of percent error from like normalized, right? So There. Wrong button. All right. So, So the way to think about this, right? These are variances from the calibration standard, and what they signify is that if I had an example bud that was tested with the calibration standard that all the labs agreed upon, and then I tested that same bud with one of these other certified reference materials, here's how big a difference it would be. And what's really important to note is that a couple of these are underformulated by such a large amount that they would really change the apparent total THC by a lot. And it's also important to note that the two worst ones had really clear signatures of contamination and degradation. And so any sort of competent procedure that was properly done would have caught that as an error. But it's an exploitable error. So that's about the end of what I'll talk about for kind of comparing CRMs to each other, because now I really want to focus again on the error involved in the lab operations themselves and talking about this concept of fit to purpose. So, all right, I mentioned, right, that there were, quite a few deviations of each lab's sort of turned in number from the consensus, right? And we could see that spread with those colored dots. So here's how that looks in a different way. Again, binning up the number of measurements and how close they came to consensus. So that x-axis is the counts, or actually the number of compounds measured, the number of products. And I've broken this down by lab. And what you can see is that the labs perform differently. All right. Lab D had the tightest distribution. All right. They were the most precise. Lab C had a systematic error. All right. Their average deviation was plus 1.93%. All right. So nearly 2%. And a couple of these others were more similar. So I think this gives us a pretty good sense, in a way, of like the precision that we can expect from testing labs. And what you can see is that even when there's no matrix involved and all they're doing is a single step dilution, and again, this is convoluted with this is to some degree still convoluted with error between CRMs, but, or say like differences, I would say this is assuming that each lab received comparable products and that the error between labs, say, comes all from labs. All right. So it's a little bit of it's not the best assumption. But we have some evidence of what share of the error does come from the labs. So, to break that down, all right, I'll go back to the original data that was turned into me from each lab. All right. And so this is actually just one example. And, it's quite a big project to come up with a sort of a universal, result from all of this, that's easy to show in one slide. But here I am going back again to just the injections, all the 9 injections from the 3 different dilutions that one lab performed on one mix product, all right? So in this mix, there were 8 compounds, and so there are 8 colored dots here that show you the concentrations measured, or actually their absorbance is measured, right? This is going all the way back to their raw, normalized absorbance data. Concentrations, right? And so what this is showing you, all right, is that for the first solution, all 3 injections came in pretty close together, like you would expect, right? I mean, it's an auto-injector. It's probably pretty precise. The second solution was made pretty consistently with the first solution. There's very little difference in the values that came in. But the third solution shows this big jump, all right? And all the dots jump. So that's like one of my favorite terms in chemistry is correlation, or in statistics is covariance. And that is a great example of covariance. And that is one of the most useful things that we learned from testing mixes, is we could actually see that nearly all of the error came from the operation when a human being made that dilution. So, and it's significant, right? It's a couple, it's just a couple of percent, right? It's not that much, but it's enough. So, all right, so we'll hold that in mind. But again, let's go back to that idea of like THC inflation and if CRMs are involved, right? Or how I would determine that CRMs are involved. So here I have results from a bunch of shelf testing that was also actually performed by Josh Sweeter, Zach Eisenberg. It was Infinite Cal and Resco Labs. And this time I've plotted the results as differences between the label and the actual measurement on the y-axis. So you can see the actual measurements are almost all lower than the label. There was one that was above. That's interesting. I've also seen that once. And then again, on the x-axis is sort of the number of results, and this was out of a total of about 150 results, I think. So pretty good statistics. And here, so if certified reference materials, or say when I'm looking at a spread like this, if I'm looking for a responsibility of a particular offset from the label as a big culprit, then I would look for like a spike in here. And if I'm looking at more like a spread, then I think that maybe THC inflation is more selective or case by case, right? I don't see one standard amount of inflation. So that would be sort of how you would look at that. And then here's another graph that's from, this is one of my all-time favorites because it's so evocative. All right, thanks, Yasha. This is a beautiful graph. All right, this is results of THCA percentages from a lab in Maryland over a certain amount of time. I didn't write it down on the slide, but it was about a year. Again, frequencies this time are on the y-axis, and the THC that they measured is on the x-axis. And what you can see is there are really big bumps, right, at certain like characteristic price points, like at about 20% and 25% and 30%, right? And so I want to point out that you could achieve a graph like that just by milking the error. You could. I'm not saying that you do, but you could, because it looks like the error in these measurements is on the order of like 5% of the value, right, often, and that's in well-run labs. So, right, so there's actually, and I could achieve a graph like this just bumping things up like a few percent at a time, maybe, right? So I'm not saying that that's not what people always do, but it's actually one mechanism that could happen. And it seems like there's enough error in this that, you might have to work at or measure a few times to really be sure. I do want to point out that the error that we saw from these labs was remarkably random, right? I mean, I saw small systematic deviations like I mentioned, but for the most part, it obeyed like Poisson statistics. The more answers we accumulated, the better the consensus got. No lab did better than the average. So those are really important points for how error between labs behaves in ideal cases. And so the last thing that I'll talk about is maybe a little more about how we define error and how we think about it, because I didn't realize that everybody thought about this, or that some people think about this differently. When I started this, I didn't know that much about certified reference materials. So I know a lot more now. Thanks, guys. So when I think of error, I think really phenomenologically. Like I take all my results, and my favorite two things to do are do root mean square deviation and average deviation. I learned it in general chemistry, and I learned it that way. We didn't even talk in terms of standard deviation. I didn't know that term till later. But for me, these are like really simple and evocative and, I don't know, deep in my heart. So that's the way I think about error. very phenomenologically. All right, but when people make instruments or CRMs, they sometimes think in terms of like uncertainty budgets, and they're similar, but they're kind of built from the ground up in a different way. To me, it feels like they involve more assumptions, but they because they might involve some kind of ideal cases or not take into consideration all the factors in the real world. So, for example, right, the uncertainty budget on like a high precision balance, they often say it's like plus or minus a tenth of a milligram, right? So, pretty tight, it seems, right? But in a real lab, or even in my living room, I can like use the force to like really change the value on my balance, all right? I did this myself. All right, like I willed it to change and I never touched it, all right? But the force I'm using is not like the force, it's the electrostatic force. And at the scales which we are weighing out our CRMs, the electrostatic force is way stronger than the gravitational force, which is what I'm using to measure their mass, all right? By like a lot. All right, so that's a little bit of physics, right? We're handling these valuable CRM solutions like a tenth of a milliliter at a time, which is really tiny, and they're really subject to electrostatic charges that build up on every single surface in the universe. So, yeah, so that's what happens. That's your problem even before you consider matrix, and then when you consider matrix, I got all kinds of problems like the keef, like really statically sticking sometimes, all right? And so my point in bringing it up is that all of these problems really scale, all right? The smaller the scale I work at, the bigger these problems are. And that's why, like, all of my easy chemistry experiments I did in sophomore organic chemistry were done at multi-gram scale, all right? Because at multi-gram scale, it didn't matter that much any of these little variations. So when we're thinking about the way we measure weed and whether it's fit to purpose, I think we may have never really defined what the purpose was. And I think we have to, all right? Because if the purpose is to like educate the consumer and give them some idea, you could give them like a really rough range, right? If they're dosing a medication, they may have some more expectation of precision. I don't know if we test the levels of cannabinoids in cannabis products. I don't know how much public health is really the reason or not, actually, anymore. I'm not sure what public health, I'm becoming less convinced that I think it does yield some public health benefit, or can, but I'm becoming a little less convinced about some of it. Or are we trying to establish the values of commodities? All right? Is that the real purpose of this? Because if we're establishing the values of commodities, it makes a lot more sense that people are manipulating it. Right, so that's definitely involved for some people, but I don't think we have a consensus of what the purpose is. I think different people think of the purpose differently. And then when we have different products, like obviously when we have produce, like flour, I mean, do I need a CRM with 4 decimal places of certainty? I don't, right? So maybe I could spend less money and use more and get better accuracy. Or like if I have some high value product like distillate and I'm trying to establish its value, I think you would be an idiot to do one measurement, right? If it's worth that much to you and the value has that, and the precise result has that much value, then you should measure it multiple times. And then you'll get a better result. Like now we know that this is actually stochastic. All right. So anyway, those are the thoughts that I would like to leave people with. And now I'd like to open the floor to any discussion or questions. So thank you very much for your time.